Have you ever wondered how pipes work in the terminal? Or have you been actually searching for something that explains you how to master pipes in the terminal? However, before going into some more complex examples, I would like to bring us all onto some common ground so that we all have some common understanding of what we are talking about. With this said, in this video I would like to talk about processes first, like what is a process? And of course we all know, of course, what a process is, but let's find out. Next one is what are files? And of course we all know what regular files are, like text files. But there's more to it. In UNIX especially you say everything is a file. But what does this mean? And is really everything a file? And with this one attached, of course, we also need to know what a file descriptor is, which also is really interesting from the point of view of a user. Especially from the point of view of a user, you may want to know about the standard file descriptors, so the standard I/O. And then we can actually start talking about pipes. So in case you just want to fast forward, use the chapter system and just jump forward. Otherwise, we will find out. So once we understood in theory what pipes are, I would like to give some real-world examples to things that happened to me, which are all multi-line examples. And I would like to explain each and every one of these and give also hopefully some hint on how you can create these things yourself. So let's dive into it. Processes in Unix and Linux. We can see processes as an instantiation of a executable program on your file system. And without going too much into the details of what a process is, so I don't want to bore you too much, the one thing we probably want to know is, every process has a process ID and some environment variables attached to it. That's the one you probably know from your bash RC, etc. And that's the most interesting part, it is having a file descriptor table. And the file descriptor table we can actually imagine like a hash map from some positive number to some actual opened file. But what opened file can these be? It's not just, regular text files. That's the next part. So the other interesting thing to know is that when a process is created, it is not necessarily just created out of nowhere, except as bin init. So except the very first process your Unix system is booting, everything else is not created out of nowhere. So if you want to actually create a new process, you first clone yourself and then you prepare your child process, which is a clone of yourself in a way you want to. For example, maybe you close some files and you rename some environment variables or whatever. And then comes the most interesting part. If you actually want to spawn a new process, so not just, a clone of yourself, then you're using the exec system call to replace the current image with the new image, with the instantiation of the new image. However, things like file descriptor table will be preserved. So you can actually inject things into the file descriptor table of the process to be instantiated. And that is what, for example, your shell is making use of. And that is how pipes are later on in this video being created. So files in Unix and Linux. There's a really famous saying in the Unix world, which is everything is a file. In Unix, everything is a file. But what is everything? Of course, your text files are files, but they do not necessarily need to be physically present on some hard disk. They can also be in memory. But because we like to categorize, we also have directories. And a directory on file system level internally is nothing more than a regular file, except that it's not exposed as a regular file, but as a directory. And internally it's containing text, like you can think of it as a CSV file with two columns, and the first column contains the name and the second column contains an I number. And the name is basically all the file names of your child elements in this particular directory, and the I number is the identification number which is unique to this instance of this file system, most likely on your hard disk, to uniquely identify this given file. This file does not necessarily have to be a text file again, like a regular file. It can again be a directory, and now we can create hierarchy. But we also have special files such as devices, and that's actually probably the thing that amazed me the most when I started with Linux like 30 years ago or so, that even your printer is a file, your mouse is a file, your GPU is a file, your hard disk can be accessed as a file, but even your memory can be accessed as a file. So, but we also have a little bit more special purpose files For example, your network communication can be expressed as a file. But on the more generous side, what is more interesting now also with respect to pipes is the anonymous pipes. In Unix, you can create a pipe, which is a pair of file descriptors, and can use them to communicate with each other. On one end, you read what you have been writing on the other end. But also your terminal is communicating through some file descriptors to your client applications, such as your shell. So what are file descriptors? Well, file descriptors are positive integer values which you can see as handles to a opened file on your file system, or one of these APIs we have been just describing. And one thing to note is that this resource is limited, typically up to 256, and that we also have some standard file descriptors. File descriptors are process local, so file descriptor 1 in process A is not file descriptor 1 in process B, while file descriptor 1, just like 0 and 2, are having some special meaning, usually at least. So file descriptor number 42 in process A is not necessarily file descriptor 42 in process B, just because they are the same number, but it's a different process and therefore a different file descriptor API and therefore a different file descriptor table. And they may still be, there can be two processes having the very same file open and having the same file descriptor even for that. But this is only possible if you have been forking off a process and the parent process has been explicitly making sure that this given file descriptor is inherited to the child process and being passed over to it. There's an alternative way how you can pass file descriptors to other processes which you do not own, which you do not create, but that's out of scope of this video, I guess. Standard file descriptors. So on Unix, and fun fact, this also includes Windows here, we have 3 standard file descriptors which are 0, 1 and 2, which stand for standard input, output and error. That basically means that on file descriptor number 0, you will receive keyboard events. Typically it's keyboard events because you're typing into your keyboard in order to, for example, type in your name and have the given program know your name in case it asks for a name. You can redirect this input and then it's not necessarily your keyboard input anymore, but this is what file descriptor 0 is typically used for. On file descriptor number 1, we write the standard output of the given program. So if it's the echo program, it is the parameter of the echo command is going to be printed to file descriptor number 1. On file descriptor number 2, typically, but not necessarily, you will see error messages. So whenever a program wants to print an error message, it is typically using file descriptor number 2 to let you know about it. Well, the fun fact here is that if this process is being classically spawned on your shell, every of these file descriptors for your process are the same. 0 equals 1 equals 2. And this is because they're all pointing to the same terminal. So when the terminal spawns a new process, it is going to first create a new PTY, which is going to give the terminal 2 file descriptors, one for the terminal itself and one for the process to be spawned. And the one file descriptor it gets for this given process, it's going to, you could say it's going to rename this file descriptor number to 0, 1 and 2. And how is it going to rename them? Well, it's using the dub2 system call. And what dub2 is doing, it's receiving 2 parameters as input. The first parameter is the file descriptor to be cloned or to be duplicated, which is the pty slave file descriptor. And the second one will then be one of 0, 1 and 2. So it's calling this function 3 times. And then it's going to close the actual slave file descriptor because it doesn't need it anymore. It's having it already 3 times, just with a different number. And this is probably a little bit important to know because it becomes more important later on when we talk about pipes. So please remember this. So the question is, why do we have 3 different then if they're all the same? Why do we have 3 numbers like 0, 1 and 2 if they all point to the same slave PTY ID? Well, wait and see. Pipes in a shell. Yes, finally. So pipes in the shells is one way to communicate from one process to another. So what your shell is doing when you want to spawn a pipe B, which means you spawn process A and want process A's output to be piped into process B's input. It's spawning both processes, and it's also creating a pipe, and this pipe on the one end it's connecting to the output of process A, and on the other end of the pipe it's connecting it to the input of process B, such that process A and B can one-way communicate to each other. Why do we do this? Well, process A can now produce the output you would otherwise see on standard output, and process B will receive this output as input as if you would have typed it into your keyboard. And when does process B know that process A has finished producing output? Well, process A will close the file descriptor, say file descriptor number 1. And when this one is closed, the other process B cannot read anymore. It actually finds out, oh, it's closed, the endpoint, so I stop reading. So in a shell, especially, pipes are represented as numbers. So just have a look at our tiny little cut command here. And this cut command here is actually printing out the contents of the given file /etc/non-existent. And I named it like that because this file is non-existent. So if I would pipe this one now, let's just do this. Cut etc non-existent, and if I would cut this out, it's telling us no such file directory, which makes sense. So now I said I would like to pipe the output to the input of the command cause. What will happen? What will we see? Let's find out. Well, cut is still producing the error message, and the cause command actually printed nothing, and it doesn't even look nice. It's probably a bug in cause command, but I don't care that much now. It's actually bad because I wanted to have this error message inside of the speech bubble of the cow. So how can we get that working? Well, if we look here again, I was also redirecting the standard error output to standard output. So I was redirecting file descriptor number 2 to file descriptor number 1, such that when you write to 2, it's going to write to 1. And since file descriptor number 1, we are then again redirecting to the input of the process cause, we are effectively also writing the error to cause, which is exactly what we want. And now I can actually give the output here, which looks like this. And that is exactly what I wanted to see. Now let's apply this real-world knowledge a bit. Now let's apply our little knowledge a bit and see if we can understand the examples I've been actually producing here. So let's start with a fairly simple one. And this command actually happens to me not too often, but often enough such that I will never forget eventually. So what this command is doing, it is basically searching in this given directory for every header file and C++ source implementation file, and whatever it finds, it is going to execute the process cut on it. And what cut is doing, of course, it takes this parameter, like this file name, and prints the contents of this file to standard output, so to standard file descriptor number 1. And what the total of this command is basically doing is it's cutting out every source and header file in my project. And this standard output I want to be connected to the standard input of my WC command here, but I don't want to have the word count, but instead I want to have the line count. So I want to count the number of lines in my project. Let's execute it. 74k thousand of lines of code. But this most likely contains also white space lines. I don't want to have these. So let's modify our command a bit, which looks like this. I was injecting one more thing here. So the standard output of our cut command inside of the find command, we want to have now filtered out every empty line. This is a regex here, which we want to invert. And then what the standard output of this grep will be is every non-empty line. And that one we're going to pipe into the standard input of the WC command. And then we want to have the line count again. So let's find out. 64k lines of code. That's a nice number. Next one. That's actually a really interesting one because this happened to me during my DevOps times when our boss came to us and asked like, oh, we have so much traffic going on, like all the servers are going on high load. Are we under some attackers? So what are the IP addresses which are communicating to us the most? Okay, I said like, let's find out. There's a netstart command and see all the IP addresses. And let's not go too much into the detail of it. In the end, it's all the same scheme of things we're having here, but probably to get an idea of how to approach to such commands in order to understand them, let's just execute them incrementally. So let's open a new shell here again. And in my case, it's probably not looking that interesting because I'm just a desktop host here. Okay, that's the output. Now I am only interested in the 5th column, which is actually the column of the foreign addresses, the IP addresses I'm talking to. So let's actually do this. I'm copy and pasting a bit here and move this over. Okay, now I'm having the target IP addresses, but also these headers here. I don't want to see these or this stuff. Yeah, I'm not interested in this one. So what we can now do is we take the next line, which is now not excluding, but including the regular expression match of every hexadecimal digit at the beginning of a line. Great. Now we have all IP addresses, but I actually want to see the frequency, like which IP address am I talking the most to. So let's first sort numerically, sort -n, n stands for numerically, and now I want to eliminate all duplicates. So for that one, I use the unique command and do not just eliminate the duplicates, but also prefix each line with the frequency, like this term occurred like 1 times or like 5 times. So let's do this. And now it looks like this. Oh, how boring, because I'm a desktop machine, but we get the point. Okay, now I actually want to sort again and numerically and in reverse order so that the most often one is actually on top. And I'm only interested in the top 5 of these. Just imagine this would be a web server and now it looks like this. Oof, but we always had this line here and I said like top 5. Why am I seeing 7 lines like these 5 plus this 2 here? Well, this is because this output here the whole time was actually going through file descriptor number 1, whereas this text was going through file descriptor number 2. So it was directly printed out, and never took part of any of this pipe chain here. Which process was actually producing this? Well, in our case, it's kind of trivial. It was netstart. And now I am going to redirect the file descriptor number 2, which is standard error, to, I usually do this one, def null. So I'm not interested in this. Just put it to the special device def null, which is like a trash can. And that's what we're having. The next command I actually made up out of my head. That's not a weird word example that I'm regularly doing, but I thought like maybe I can also provide some more data scientist approach command that you could do these things on a command line too. And I was asking myself, what are the most often used C++ include directives in my own project? And of course, I again start with the find command. And again, I look at all my header and implementation files and I execute cut on these. But now I'm going to filter on the string hash include such that I'm only seeing all the include lines. And now I know that they all start with include. I don't want to see that include term each and every time. So I'm going to whip it off by only printing the second term. There are now different ways how to do this. I chose this one because I precisely know how I construct my lines. And then I'm going to sort these because again, these two lines belong to each other actually. I first sort and then I eliminate all duplicates again and put the frequency of each occurrence in front of it. And now I do the same trick as in the last command. I sort -nr again such that I'm getting some kind of a nice frequency ladder and I only want to see the first top 5 of these, and now I know which include directive I use the most often, which is FMT format followed by string view and by array, which is actually good. It kind of indicates me that my project apparently is in good shape. I'm using the right headers here. It's not meaning too much though. The last weird example that happened to me just a few days ago when I did my first attempt on recording this video, it is actually now the 3rd attempt, is when I realized my file naming scheme isn't really actually the greatest one. Because in my editing process, a few of these files I all named with result-something. And then I realized I don't need this result prefix there. So let's get rid of it. And there are probably some tools on the internet which help you in batch renaming. It's actually even a feature for them to batch rename files, but I don't need them. I can do it just in my shell. So in my case, I was just quick and dirty going into my shell. Like I did right click in my graphical file manager and said like open a terminal here. And then I started typing ls-1, which basically means list me the files, but only each file once per line. So only one file per line and only the file name for this given directory here. And now I am of course using a demo directory here. And now I'm interested in the first column which is the file name. There's only one column, but I'm going to duplicate this value so that I'm seeing the file A like AA in each line, and B as BB, and C as CC, etc. So then I'm actually doing my foo on it, because I am going to replace the second term result-a something with only a something. So the result prefix is going to be deleted on the second column. And with this output, I am now going to feed it into the while command. So with this output, it already looks quite great. Let's actually have a look at this. Let's have a look at this. It looks like this now, but now I actually want to operate on it because I want to MV the first column into the second column, right? So for that, I'm using the while statement, which in its condition actually invokes the built-in read command, which is then reading from standard input, which is the standard output of the SED command from the one we have piped into it. And this one is giving me each line, and it's storing the result into the args environment variable, which I am then using to actually construct my MV command here to rename the first column into the second column. But of course, since this one is just a demo and I want to see the output, what it would do, I actually prefixed it with the term echo here. So that's the output. And if you construct things like these, you may make mistakes. These happen to me too. And what I do usually is I'm doing a dry run by first always putting the echo here and then incrementally writing it until it works. Like for the simple one, it usually works on the first time, but maybe it's the second time sometimes. And when I'm comfortable with the output, I just delete the echo here and then I'm executing it. So I mentioned redirecting quite a few times already. And I would like to give some special mention here to this one because maybe it's not that obvious. So in this case, I'm spawning the cut command, which is going to cut the text file called sum_file.txt, and it is usually writing to stdout, which is file descriptor 1. But what if there's some circumstance where you want to have this output be redirected to some other file descriptor, which you know ahead of course, what file descriptor this one is. And in my case, it is file descriptor number 3. So the one actually is the output file descriptor you want to redirect, and you want to redirect into file descriptor number 3. And in order to tell the shell that we are talking about numbers here, about file descriptor numbers, that's on the right-hand side. That is why we put the ampersand here. It's not the greatest syntax. It's not my invention. So with these kind of syntax, always take care. Always double read if you're right, because it's so easy to accidentally mix around the left-hand side and the right-hand side. And yeah, just be aware of this. Do not try on a production machine until you have tried it at home. Then you can try on a production machine. To recap, pipes in a shell are extremely powerful and even easy to understand once understood what file descriptor tables are and how pipes are constructed. The biggest takeaway, hopefully, is that A pipe B will link A's standard output to B's standard input using a kernel pipe. Standard file descriptors 0, 1, and 2 are most important to know about and can be redirected or muted at your own will. Did you actually know that in Bash you can do TCP programming? Well, that sounds like worth talking about, most likely in another video. So many thanks for watching. You obviously made it this far into the video, which apparently took way longer to describe all the bits and pieces that I think are really important to actually master the pipes in a shell. If you like this somewhat more advanced content, I'd be really happy if you would tell me what kind of Linux and terminal related content you would love to see from me. Many thanks. See you next time.